Hello and welcome to our webinar, Gravimetric Extrusion Control for Pipe and Tubing Production, presented by Conair. I'm Jim Colari, Editorial Director of Plastics Technology, and I will be your moderator. Consistent quality is paramount in the production of pipe and tubing. Additionally, significant material savings can be obtained by tightly controlling product dimensions with the correct process equipment. In this webinar, Conair will cover gravimetric control of an extruder and production line speed to ensure optimal quality and cost savings are achieved in your product run. A detailed discussion of the upstream material handling system includes blending resins upstream of the feed throat, detection of the extruder rate at the throat, control of the extruder RPM, and control of the product itself in feet per minute, all accomplished with a simple recipe configuration, which includes product weight per length desired and production line speed. Our presenter today is Alan Landers, Conair's blending product manager. Alan has 33 years of machine design experience focused on blending, material conveying, and scrap recovery systems for extrusion and injection molding processors. His prior experience as a test engineer, engineering manager, and product manager provides him with the unique skills required for analyzing difficult process problems and designing unique machine solutions. He has extensive experience in applying data collection techniques with an emphasis on numerous auxiliary equipment systems such as blending, temperature control, drying, and conveying systems. Please feel free to ask questions at any time during Alan's talk by typing them into the panel on the right-hand side of your screen. We will address as many of your questions to Alan as time allows following his presentation. I'd now like to turn the webinar over to Alan Landers.
Thank you, Jim, and welcome everybody. So to get us started, I have a couple samples of a picture here of some different pipes, and the good thing about gravimetric extrusion control is the system itself doesn't really care what the pipe is for, whether it's gas or water or a simple conduit, various sizes. It works equally well across the entire spectrum of products. And with these pipe products or tubing, they have two control specifications that a processor is concerned about. And the obvious, of course, is the inside and outside diameter, which translates to a wall thickness of the product you're trying to make. And then a secondary quality check that they do is how much does that pipe weigh per foot? So if they have the right ID and the wall thickness is there, the weight of the pipe per foot is predictable, and I'll cover a formula a little later in the presentation that sort of brings all this together and describes how the two are interrelated. So again, the idea here is to create tighter tolerances. You want to run a pipe close as to its minimum specification parameters as possible without giving plastic away. You don't need the pipe to be heavier than it needs to be. You don't need the wall thickness to be any larger, and of course smaller than the specification allows. And the closer you can run, that's dollar savings. So you're just an example here at the bottom is whatever you can do to minimize this variation is material savings as well as time savings. So there's quite a payoff to getting the system operating quickly to its target and then on specification. So here's a layout of a typical pipe or tubing line. The basics are, of course, sometimes there's a dryer involved for drying the material, other times there's not. And then there's, of course, an extruder there with a pellet material supply going into the throat of the extruder. And we're going to replace that material supply hopper with a gravimetric loss and weight hopper, which you'll see later in the presentation. And of course, the extruder, it has its zone temperatures down the barrel where it heats up the material and melts it and comes out of a die and then it transitions through a sizing plate or a sleeve, they call it, to get the pipe into its initial shape. Of course, coming out of the die, it's just a simple melted flow of material, but it needs to be sized across this cooled sizing plate. And then from there, it goes into a vacuum sizing chamber, which of course Conair has sold for many years, which is for precision control of the diameter and the wall thickness through the application of a vacuum on the chamber itself. And then after that, it's just cooling. You need a particular length of cooling to make sure that the pipe is a complete solid before it goes into the puller and ultimately to some type of cutting unit or a spool that rolls it up or cuts it to length in sections. Some products coil easily like a conduit, so they end up in rolls. You've probably seen these in applications on the side of the road. A very common one is the orange telecommunication conduits that are sold. You see a lot of that being installed around the country now. And then others might be water pipes where they're not so flexible. They're just cut to length and sold in lengths for handling purposes. So you got some challenges with a system like this. You can control precisely through the application of vacuum, an OD and an ID, and the sizing tool of a product. But that system doesn't work unless you supply it with the correct amount of plastic. You've got to have the right amount of material there. If you don't have enough plastic coming into the vacuum sizing chamber and the sizing plate, for instance, if it's not enough, then you're not going to get the right weight per length. You're not going to get the right OD/ID. It's going to be too small. And conversely, if it is too much plastic, then there's not enough vacuum in the world that's going to reduce it. So overages of the supply coming from the extruder and the die is a problem that without gravimetric extrusion control, the operator has to deal with that. They have to figure out what the extruder speed should be to give the right amount of plastic. And then you've got the added issue of the speed of the line that's produced by the puller. If the speed is too fast, the product becomes too thin. If the speed on the puller is too slow, the product becomes too thick. So you've got all these variables. You've got the extruder speed, you've got the puller speed, you've got the vacuum tank. All these things rely on the correct supply of plastic coming into the process. So we're going to solve the problem of the extruder speed and the puller speed through the gravimetrics. So keep this in mind as we talk about the process of this picture in your head. So this is a cross-sectional view of the outlet of the extruder. The material melted would come in where you see the little blue part, and then it would go through the die itself so that it's extruded out roughly in the shape that you'd want the pipe to be. And from this point, you can see it positioned there on the left. It would go into this brass ring, which is the very entrance to the vacuum tank for more precise sizing of the plastic itself. So this is important to have what's being extruded take on its initial shape before it goes into the cooling in the vacuum tank. And then, of course, you've got the vacuum tank itself. You can see the brass ring on the far right where it enters into the vacuum tank, and then more or less vacuum is applied to precisely control the vacuum applied to the product to get your OD and ID and subsequently wall thickness correct. And then from there, it goes into subsequent cooling tanks. There could be one additional cooling tank. There might be 3 or 4. There could even be more, depending on the size of the pipe and the amount of cooling required to have it be a solid product by the time it's introduced into the puller and pulled off for shipment. So the vacuum size tank basics is that we have issues, processors have issues where you can have the tubing size fluctuate if the vacuum applied to the tube is not precisely controlled. In Conair's vacuum tank, it applies a vacuum in a separate reservoir, and then it's plumbed into the upper tank where the product is located. And we've discovered that that actual secondary tank helps minimize the surging of the vacuum amount that's applied to the product by having sort of this secondary reservoir for precision diameter control through the vacuum itself. And there's 3 different ways to control the vacuum. One is just a simple speed dial, where the operator manually controls the vacuum through adjusting the speed of the vacuum pump up and down. Very basic. It's the oldest way to control the vacuum motor and the pump speed to increase or decrease the amount of vacuum applied to the product. And then the second one we call precision auto vacuum control, Conair's PAVC system. And that uses an HMI system for fine-tuning the vacuum applied, where the operator can actually type in the amount of vacuum he wants to do 2 decimal places, as opposed to just turning a speed dial and looking at some indicator on how much vacuum is applied to the system. And then the computer on this particular feature would automatically control the vacuum to fine-tune, to track to the vacuum setting that the operator's entered through the HMI. There is an optional capability to communicate to a wall unit, a gauging system, some people call it, that monitors the OD of the tubing gauge itself. And the gauge itself would be in control of the vacuum that way, so that you can use the system automatically in the computer to control based on the feedback of the measurement that's occurring from the gauging device to control the vacuum, to precisely control it, taking adjustments completely away from the operator, where he doesn't have to worry about it. So these systems in 3 different methods are used for precision. But as I stated earlier, it really matters that you have the right amount of plastic coming into that tooling device and into that vacuum chamber. Too much material, it's not going to work. Too little material, again, it won't work and control precisely. And then finally, after the vacuum tank and the cooling tanks, you've got a puller device such as this. Conair's puller assembly is shown here, and that controls the speed of the line. How quickly do we want to produce the product in feet per minute? And the operator sets this too. So you can see there's a lot of things the operator has to deal with in order to end up with a quality product. The extruder speed, the vacuum speed, and the puller speed all affect the quality of the product. So the more you can automate a production line like this, the better. So some of the production concerns with pipe extrusion, you can see on the top right, that's a picture of a die with the extruder coming from the right and pushing through a screen pack, for instance. So one of the things that happens in a screen pack is it slowly clogs up with different particles and things that they're trying to keep out of the die. And that affects the yield. It affects how fast you can go, because as that screen pack becomes full of particulates, the rate of the extruder pushing plastic out in pounds per hour starts to drop. And it's just another variable the operator has to monitor through some type of QA analysis of the pipe that he's producing, which unfortunately is all the way at the far end after the puller. He doesn't really have control directly at the die without a gravimetric product there to control the rate of the extruder. So what you'll see as the screen pack slowly clogs is the PSI in the extruder rises. In order to maintain the pounds per hour, you typically increase the extruder speed. But more commonly, an operator will rely on maintaining his product quality by slowing down the puller. He's got less plastic coming out of the extruder. Instead of fine-tuning that, he'll go to the puller and slow it down, which of course is less feet per minute. So that's lost time. He's not making the product at the same feet per minute that he normally would, and he's losing time. He's losing yield, is what they call it. So, you know, the results of things like this, the gauge falls off. If you have a multi-layer system where there may be more than one extruder, pushing plastic into the same die for different layers of a pipe, now you've got two extruders you've got to deal with to keep the extruder ratios correct. And of course, all this creates costly scrap and shutdowns and poor quality and non-uniform products. And as I mentioned, the screen package is the screen pack blockage is the most common cause of this. Longer term, you have screw and barrel wear, which is really unknown to a processor, but a gravimetric system can see that, and it will adjust the extruder speed over time. So 1 year, it might be something in particular pounds per hour per RPM, and as this screw and barrel wear occurs, that compromises the rate of the extruder, but the gravimetric system knows that, and it would simply just adjust the extruder motor speed to maintain that. And then finally, you've got different effects of the way the plastic is melted, changes in temperature, viscosity, back pressures created by the adjustment of the tooling, and things like that. So there's a lot of variables that go into keeping this product correct, and the idea being that a gravimetric system, along with the vacuum sizing tool and tank, can keep you your product on spec. So some basics of a gravimetric system is, you know, this is shown here with a gravimetric hopper at the very bottom, and that would be mounted on the extruder throat. But you could put a blender right above that, as shown in this picture, and the operator would simply enter the typical resin recipe that he'd like to go into the extruder, and that's something all of you are very familiar with general purpose type blenders, of which Conair makes continuous as well as batch blenders. So there's a supply of the material that's blended if required by a gravimetric blender and then conveyed to this gravimetric hopper. The gravimetric blender could be mounted offline, for instance. It could be on a stand, floor mounted, well away from the extruder, and material could be conveyed over to the gravimetric hopper on the extruder as well. Or it could be positioned just above it like you see here, or on a mezzanine above. Lower rate lines are most commonly outfitted with a blender directly above the extruder hopper. If they're higher rate lines, the blenders become rather large, and it's just more convenient to have them located separately on a stand offline. So the next thing we're going to do is, after we have this blended recipe from the blender come to the extruder hopper, we're going to detect the extruder rate, pounds per hour, at the throat using that extruder hopper. And we're going to use that rate calculation to control the RPM of the extruder so that we get the pounds per hour that we want. And the system also will control the puller speed in feet per minute. So the line recipe becomes very simple for the operator. He simply enters how many pounds per foot he wants the product to weigh and how many feet per minute he'd like to run the line. So as you can see from our earlier graphic, we talked about all these variables of getting the vacuum system to work properly for fine-tuning the gauge. We had the problem of the extruder speed. Operators don't really know exactly where to set it and how to maintain the rate as the extruder speed needs to be changed. Changing the feet per minute, of course, throws everything off, and he's got to readjust not only the feet per minute, but the extruder speed as well to get the right supply so the vacuum sizing tools and the pump tank can do what they're designed to do. So the line recipe is just a calculation. It's based on pounds per hour at the feed throat using that extruder hopper you see at the very bottom. So here's a couple of installations of a gravimetric weigh hopper. You can see the extruder positioned at the very bottom. Quite often there's a drawer magnet there. And then above that, you see in that black frame is the loss and weight hopper with a little sight glass on it. And at the very top, you see a vacuum loader where it's pulling the material from a blender positioned. You can see in the background they're well away from this, and they're just conveyed over to this system. So the vacuum loader just keeps the vessel directly below that full all the time, and then below that surge hopper there is a knife gate that opens and closes as material is needed to replenish the level within the loss and weight hopper. So this is a typical stack up. The one on the left is sort of a smaller rate extruder, might be up to 300 or 400 pounds an hour, where the one on the right is a larger hopper, which could do probably up to 2,500 pounds an hour. Similar stack up, just a little bit larger for volume purposes. So this is what happens as the system runs in gravimetric. It loses material, and we're calculating the hopper weight over time. That's referred to as loss in weight, and we figure out how many pounds per hour that is, and that data is captured and sent to a computer. So the feed rate is equal to the loss in weight over the change in time, the change in weight over change in time. So we're just sensing the hopper weight using a load cell. As it loses material and the extruder takes it away, we divide that by the amount of time that took place, and then we end up with a feed rate in pounds per hour. And then a little graphic at the far right, you can see that if the screw RPM needs to rise, like in the example I gave you earlier with the screen pack slowly clogging, the throughput would drop. But since we have this system installed, we can detect that and increase the screw RPM so that the pounds per hour labeled throughput here over time is maintained at a constant level. So again, we've taken away the worry of what the extruder speed should be by using a system like this. The operator doesn't have to worry about it. And then when the hopper gets low, we fill it back up. And during that time, we come out of gravimetric mode because it's not able to calculate how much is leaving the hopper while it's being refilled. We call that a volumetric fill. So it fills back up. This is that knife gate opening up and filling the hopper back up. And during that time, we just leave the extruder speed alone. And then we go back into gravimetric mode as it loses weight again. Okay. So those are the basics of this type of system. It's really a very simple device. It's simply just a hopper sitting on a load cell where we're able to measure the hopper weight, and the computer calculates the pounds per hour based on how much time elapses during its loss and weight cycles. So this is a graphic showing exactly what's going on. You can see the computer control panels over to the right. It takes that data from the loss and weight hopper, which is the change in weight over change in time, or pounds per hour. And with that information, we change the extruder speed. You can see there in the center with the green arrow, control the extruder RPM to a desired pounds per hour. And then we also control the haul off speed, because ultimately what we're after here is a particular pounds per foot. And in this example, we're after 0.473 pounds per foot. And the operator's running this line at 25 feet per minute. Now there's a wide range of different products. Some products run 100 feet per minute, some run higher, some run lower. And as you can imagine, the limitation on a line like this is cooling. If you make a huge pipe, it takes a lot more time to cool. So you have to run it a lot slower so that it's exposed to the water tanks and the vacuum tank for a longer period of time to solidify the product. So bigger pipes typically have slower feet per minute. Smaller pipes have much higher feet per minute. This is sort of a medium range conduit pipe as an example. And you can see that extruder rate in pounds per hour equates out to 709.5 pounds per hour. And that is a direct result of the computer being told to run a 0.473 pound per foot product at 25 feet per minute. The computer automatically knows that has to be 709.5 pounds per hour. If he were to change the line speed, for instance, from 25 feet per minute, but he keeps the product spec at 0.473 pounds per foot, then obviously you need more plastic, and the extruder rate would be adjusted upward if the feet per minute, of course, went up. If the feet per minute went down, then of course you'd have to lower the extruder rate below 709.5 pounds per hour, all with the goal of maintaining that 0.473 pounds per foot. So this whole system is now taking control of the extruder speed. It's setting the feet per minute that the operator entered, and it has taken all the guesswork, or if you will, experience that an operator has to have in order to know what extruder speeds he should run and what haul-off speeds he should run for particular products to maintain a particular product spec, such as 0.473 pounds per foot. So a little bit of math here. It's nice to know, well, how does the system do this? How is a true way or a gravimetric extrusion system doing what it does? And typically, if you take the given sentence here in this example, a processor has a pipe that he's making. He has an outside diameter of 1 inch and then a wall thickness of 1/4 inch. That means that the inside diameter is 3/4 of an inch. Okay, and the length is 1 foot in this example, because we're trying to figure out how many pounds per foot this should weigh. And the desired puller speed is about 25 feet per minute. And that's dictated by the whole cooling of the system. So with that given, you can see I've got some formulas here that they're really just a geometric calculation that leads to the pounds per foot calculation and the pounds per hour calculation based on a pipe diameter and a wall thickness. So the proof is, if you take the volume of a rod instead of a pipe, it really is just the outside diameter times pi times the radius squared times the length. So our length is 1 foot. Well, the pipe volume of plastic is actually the rod volume minus the inside diameter, because there is no plastic in the center of this. So you take the rod volume, which is the outside diameter, times pi times the radius squared, and you subtract the inside diameter times pi times the radius squared times the length. So I've called that PV, which is the pipe volume of plastic, and I've converted it to metric. So I've got 2.54 centimeters, which is 1 inch, times pi, 3.14, and times the radius squared, which is the 1.6129 radius squared. And I subtract off the ID, because there is no plastic there. Same formula, I'm just subtracting off the inside diameter in centimeters times pi times the radius squared, and then times 1 foot, which is 30.38 centimeters. So the result is the pipe volume works out to this 12.8 minus the 5.4 times the 1 foot, which is 30.38 centimeters. So now you have a pipe volume of plastic, which is 2.2593 cubic centimeters. Well, what is that in weight per foot? Okay, if you think back to all your material spec sheets, there's always this grams per cc on the spec sheet that describes the plastic that you're using. In this case, I've chosen polyethylene for this example, and it has a 0.95 cc gram weight. So it weighs exactly 0.95 grams per cubic centimeter. Well, if you multiply that by the pipe volume, you end up with a weight, 214.63 grams per foot. or 0.473 pounds per foot. Now I've converted back to English units. Well, the extruder is going to set itself to the value in pounds per hour that will produce the 0.473 pounds per foot, which, of course, is dictated by how many feet per minute you're running. There's 60 minutes in an hour, so we multiply out the 0.473 pounds per foot times the 25 feet per minute production speed. There's 60 minutes in an hour, and voila, 709.5 pounds per hour. So all we've taken is a pipe specification that's an OD and an ID and a wall thickness and a desired puller speed and converted it to pounds per hour. Okay, so now you can see the weight loss system has done all this for you. It's figured out that you want to run 709.5 pounds per hour based on the 0.473 pounds per foot specification that we talked about in the second slide. You've got an OD and an ID, you got a wall thickness, but for every pipe described like that, there is a pounds per foot that corresponds to that. And this is how the quality departments of these companies arrive at the pounds per foot specification that they're actually tracking. So stay with me. I know this is a lot of detail, but I wanted people to understand that the system is automating all of this for you. So this is a picture of the extrusion control system, the home screen, and you can see by the red arrows I've drawn here, there is a weight per length that the operator entered. He set it to 0.473 pounds per foot for that 1-inch diameter pipe with a wall thickness of 0.25. He set the length per time, which is the speed of the line in feet per minute, to 25. And over to the right, you see the set weight per time. I put a check mark by that. The computer calculated the 709.5 pounds per hour, like I showed you in the formula prior to that. So we've taken a lot of variables that the operator was having to deal with: the screw RPMs, the feet per minute, how many pounds per hour do I need to run? All that stuff has been automated with this device. And as you can imagine, this is a single extruder. This would become much more complicated for an operator to deal with if he had more than one extruder pushing plastic into the same die for a multi-layer pipe. So I brought this up again just to kind of drive it home. The line recipe for the operator is simply how many pounds per foot he wants to run and how many feet per minute he wants to run that product. And our example we gave in the math was that 1-inch pipe with a 1/4-inch wall equals the 0.473 pounds per foot. And at 25 feet per minute, the computer is going to set the extruder to run 709.5 pounds per hour and automatically control the extruder speed, irrespective of what happens to the temperature control units on the extruder or the blinding over of the screen pack to catch particulates, and automatically set the puller speed for you as well. So the results of these systems, obviously, is the blended materials for each extruder are brought together. In our example, it's a single extruder, but you, again, as I mentioned, you could have more than one extruder. And then you have a line recipe for gravimetric extrusion control, which in our example was pounds per foot, and then feet per minute, using the true way gravimetric extrusion control product. And then next you have the sizing plate and the vacuum tank for the precision diameter control. Again, that product only works if you give it the right amount of plastic. So these two products together really tighten the tolerances on the product, controlling the puller speed, and then obviously a cutter at the very end to size the length of the product. And then running it closer to minimum specifications is obviously money in the bank, saving on materials, and of course labor, keeping the yield of the production line as fast as possible and is at the right quality tolerances. So a request for quote for a pipe and tubing line would be, simply what materials are you using? What are your blend ratios for your blender? what is the rate of the extruded process in terms of pounds per hour, how many feet per minute, what's the range that the puller needs to operate at, and then the gravimetric extrusion control and puller line speed control using the TrueWay gravimetric loss and weight technology. Then the vacuum sizing tank for precision OD control, whether it's manually operated or controlled by an HMI or controlled by a gauging system, it doesn't matter. That part of it is the precision part of this. The gravimetric part is the heart of it to give the right amount of plastic so that the vacuum sizing tank can do its job. And then finally, the puller with the cutter. So let me bring up the control system. This is a picture of the system that I showed you in the PowerPoint earlier. And it's a system running a single extruder in automatic. Again, just to review, you see your weight per length there at the top. It's set to 0.473. That's actually what it's doing. It has a set feet per minute of 25 feet per minute. And then you can see the extruder speed is controlling at 709.5 pounds per hour, all dictated by that geometric calculation I showed you. This is how it gets to that 709.5 pounds per hour using that math. And then you can see the extruder RPM in this example is 46.9 RPM. As the extruder speed would start to be compromised by the screen pack clogging, you would slowly see that set RPM rise a little bit in order to maintain that 709.5 pounds per hour. Conversely, if the pressure on the extruder becomes too high, the operator has to change the screen pack. So he does that on the fly, and then suddenly the RPM is too high because he's changed to a screen pack that's clean. Now the extruder pounds per hour rises. The loss and weight hopper sees that, and it will subsequently slow down the RPM of the extruder to maintain that 709.5 pounds per hour. So that's the system. We'll skip down here on the bottom right here to a button called Recipe, and I'll click on that. And this is what the operator entered. He told the line he wanted to run 25 feet per minute, and he wanted a product that's 0.473 pounds per foot. And he does this, and he clicks that automatic button, and it sets the extruder speed, and it sets the puller speed, all with the goal of delivering the right amount of plastic so the precision control conducted within the vacuum sizing tank can do its job at the highest rate possible. Okay, so now one of the nice things about this system is, remember I told you he operates at 25 feet per minute because of the cooling system that is occurring on the plastic through the vacuum tank and then through the subsequent cooling tanks prior to the puller. Well, if he has lots of cooling capacity, then why not speed this up? Why does he have to stay at 25 feet per minute? He could operate this at 26 or 27 or 30 feet per minute, keep the product at 0.473 pounds per foot, and get the job done sooner. So let's just do that. Let's just change this. And here we're changing it to 27 feet per minute. I'm going to commit that change. And I'm going to go back to the home screen. And you can see that my feet per minute now changed to 27 feet per minute. The product is set to 0.473 pounds per foot, but it increased the extruder speed from 709 to 766. It did the math for him. All they did was change the speed of the line from 25 feet per minute to 27 feet per minute. That's it. And the computer automatically knew that that had to be 766 pounds per hour in order to maintain the 0.473 pounds per foot. So that concludes the presentation. I wanted to show you this screen so that you could see real quickly how the system works and how easy it is to operate, and how all this math and the control of the extruder and the puller, the guesswork is gone. The operator now can use the computer to do all this. So I'll be glad to open this up to questions.
Thank you very much for that presentation, Alan. We do have a couple of questions to get through. Um, can the gravimetric system work in conjunction with a gauge system that monitors or controls the diameter of the pipe?
Yes, thank you, Jim. That is a good question. A gauging system that would be installed in the vacuum tank would measure the OD and the ID of the pipe as it traveled through the gauge. And that can be used in conjunction with a gravimetric system. It can be used to monitor and just display the OD and the ID based on all this math that the pounds per hour is taking place on the control of the extruder speed and based on the vacuum sizing tank to verify exactly what's happening. That's the simplest form of applying it in sort of a monitor mode. Secondly, the gauging system could be set to control the puller speed. Okay, and in that case, the gauging system would control the puller speed and increase or decrease it based on what's happening with the throughput of the extruder. The beauty of a system like that is if you have a gravimetric system controlling the pounds per hour into the extruder throat, then the gauging system really is just making very minute changes to the puller speed to keep the product on spec. If you did not have the gravimetric system to control the pounds per hour going into the extruder, for instance, and if the screen peck began to clog and the pounds per hour started dropping off, then the gauging system being control of the puller would slow the puller down in order to maintain the product specifications. That's not good because now you're losing time. You're making the right product, but you're making it slower. So having the gravimetric system working in conjunction with the gauging system is yet another way to increase your yields and have very precise control of your product quality. So the answer is yes, it can be deployed to work in conjunction and can control things, or it can be used as just a monitor type system.
Thank you. Could you discuss the type of data reporting that might be available with the gravimetric system?
Yes, there's this button I have here to the right called report. That is one particular way to get reports out of the system, and I'll show you those. Before I do that, I'm going to click on this totals button. So the system keeps track, the gravimetric system keeps track of how many pounds the system has produced, how many feet the puller has produced, and it keeps track of totals in two numbers. One we call inventory total, the other one we call shift totals. That way you can clear, say, the shift total every 8 hours or every 12 hours, whatever your shift might be. And the inventory total, maybe you'd clear that once a month or once a week or whatever. So there's totals that you can keep track of. And those are available under this report tab. In addition to the types of reports, you can select a report here, alarm reports, the shift in inventory reports that we talked about, or a total system report. The format, it can be we call formatted report, which is a easy to read format, or it could be selected to be a comma separated file that you might want to export into a factory management system for data collection. And you can select the destination. It can be a telnet connection off to a PC, or it can be the compact flash internal to the system, and you would simply run the report. These are called on-demand reports. You could also schedule any one of those reports the same way based on a schedule. You could get one every hour or every 15 minutes or once a day or whatever. And then there's also logging of the totals or the recipes that you're running. And it would every 15 seconds write out the data to a file as well. So you have a lot of choices here. In addition to these canned reports that the system produces, the product is also available to Conair's Smart Services product, which is the cloud-based management, data management, and alert system for all the Conair products. The TrueWay system would work in conjunction with the Smart Services product as well. And that's nice because you can track all the things that you see here, the extruder RPM, the weight per length, the pounds per hour, the feet per minute. All of this stuff can be trended over time in data formats that are up to 2 years in length, so that you can see and report on the very heart of the system. Being a continuous process, you could look at any moment in time and see how the system was performing.
Right. Okay, thank you.
Mhm.
What is the method to minimize the air or defect inside the pipe? I guess this means during the extrusion process or during the cooling and sizing process.
I think the main thing is that we've covered is delivering the right amount of plastic so that the precision control of the vacuum sizing tank and the tooling can do its job. So the minimal finite adjustments are done by the vacuum sizing tank and the tooling, as well as the cooling process itself. Whereas the bigger part of it, of getting the right plastic in there, is part of the TrueWay gravimetric system. So those two systems working together minimize these defects or variations that you're describing. I believe it was what the question was.
Thank you. Okay, I think that is all I see in terms of questions in the queue. So at this point in time, I'd like to say thank you to Alan Landers and to Conair for a very informative talk. I'd also like to thank all attendees for their attention and interaction. This webinar was recorded, and soon you will be receiving a link via email to the recording that will point to the webinar archives on ptonline.com. So at that point, you can listen to the webinar again in whole or in part, or you could forward the link to any of your colleagues who could not join us today. Once again, thank you to all who attended. Thank you to Alan and to Conair. This concludes our program. Goodbye.
Bye-bye. Thank you, everybody.